Start recording this one, and let's dive in here. So I mentioned that I am recording multiple things here, so I do have the ability to answer questions and write down responses and stuff like that. That's one of the things that I am recording. So if you do have a question, I could probably answer it. If not, then I'm recording my tabletop for no reason. So we have capacitance and capacitors. So this is the first electronic component that we're seeing in this class, which is interesting because typically in, say, Physics 1, you were required to study things, but they had you start with resistors and not capacitors. Capacitors make a lot more sense from electrostatic perspective. And right now we're really just going to cover them from an electrostatic perspective. And then we're going to, when we start circuits, we're going to be like, okay, here's capacitors, which we already know about. And then we'll get into resistors. And if you guys have taken an electronics course, that's cool. That's useful information. One of the things most students find about this class versus, say, an electronics class is this is way more basic than what you get in an electronics course. Like if you take an electronics course, it's like, oh, here's some components, let's start slapping them into a circuit and see what happens. When I say this is more basic, this is more for, again, more geared towards people who are not building circuits per se, but more geared towards people who are going to be building the actual capacitors. Because, when you think about it, it's like, okay, if I'm going to make a circuit that has, capacitors, resistors, and whatnot, well, somebody had to make those, so it's cool that you can start with those for a circuit, but we're starting a lot more basic. That in this class we're going to really understand capacitors and resistors, and so as a result we don't get into too much actual circuits. We'll get into very, very basic circuits in this class, but if some students ask, well, am I going to be able to build a computer? No, far from it. Just because we don't get that far. Hilarious, Oscar. Okay. So, capacitors. So what is a capacitor? Well, a capacitor is essentially just two conductors that have equal but opposite charge. And so we've kind of looked at this in previous units. And we looked at it with the electric field and we said, hey, if you got, two basic pieces of metal that are, say, pretty flat, then we'll get a nice, not even, but a uniform electric field between them. So we call these two conductors the electrodes, or sometimes we call them plates. And the whole point of a capacitor is to store the charge, okay? That we store charge, and it makes it invaluable in many different types of circuits. There's many reasons to store charge. Typically you say, okay, I'm storing charge for use later, which could be true, but it could be for different reasons. So there's many different reasons to store charge, but basically the basic reason I'm going to give is like, oh, you store it for use later, like a battery. Almost think of it like a capacitor, like a rechargeable battery. Like, oh, I can stick charge over here and then use it, down the road for something. So as it says here, the electric field strength, E, and the potential difference, delta V sub C, increase as the charge increases on each electrode. So you put more charge, you get more electric field, which also gives you more potential difference. And just like there was a special formula for the uniform electric field, there's a special formula for the potential difference. Notice this potential difference is the difference, between the two electrodes. So you could, theoretically you could calculate a voltage for each electrode individually and then subtract the two to get this potential difference. But that's what's happening here. So we say the potential difference between the electrodes is directly proportional to their charge. So stated another way, the charge of a capacitor is directly proportional to the potential difference between its electrodes. So we have this formula here written two different ways. It should probably be written a third way. Q stands for charge, and just like with the electric field, it's the charge on one of your two electrodes, because obviously if it's equal and opposite and you had two charges, the total would be zero charge between them. So this is just the charge on one electrode. It says the charge equals the capacitance times the potential difference, the voltage. So you can think about, finding the voltage on each thing individually and subtracting the two. It also shows you that the change in potential difference, or your delta V, is equal to your Q over C. Likewise, the third formula would be C equals Q over delta V. That is the definition of your capacitance. Capacitance is the charge on your capacitor divided by the potential difference between the two. And again, the potential difference would depend on the distance and all of that stuff. So we define, using this formula here, a constant of proportionality, C, and we call it the capacitance. And it's interesting to note that this formula for capacitance, which is not written here, it would be C equals Q over delta V. This formula is actually Q equals C delta V. That C is just some constant proportionality that we decided to call capacitance. And it has other formulas that we can use to calculate capacitance, but this is the basic form. So charge has units of coulombs. Voltage has units of joules per coulomb, which ends up being interesting because then that gives us a unit for capacitance of essentially being a coulomb per volt. It's also known as the farad. So long story short, the unit of capacitance is a farad. Boom. So capacitance depends on the shape, the size, and the spacing of the two electrodes, okay? Which isn't shown in that formula, but then if you start to think about that V that we looked at earlier, it's definitely in V. So the obvious charge is there, but it also depends on the shape and the size. So a capacitor with a large capacitance will simply hold more charge for a given potential than one with a small capacitance. And so that's interesting to note. You can have two capacitors that have vastly different capacitances. You can end up getting the same amount of charge on them by charging them with different voltages. Now obviously if you have a much smaller capacitor, you'd have to use a much larger voltage. But just knowing the capacitance doesn't tell you how much charge that thing has. You'd have to know, well, what voltage was it hooked up to? And if it was hooked up to a significant voltage, that capacitor could pose a significant health risk. What I meant to say. To charge a capacitor, we need to move charge from one electrode to another. So the simplest way to do this is to use a source of potential like a battery. So a battery uses internal chemistry to maintain a fixed potential between its terminals. And again, we'll talk about batteries more in the next unit because it's chemistry we have to deal with there. But essentially, not looking over the course of a year or two, the battery pretty much maintains the same potential between its terminals, while you're using it. And it uses chemistry to do that, and we're just not going to get into that right now. So typically what we do is we take a battery, we hook it up to our capacitor, and you can think of the battery as physically moving, say, negative charges from the positive plate to the negative plate. So overall, the total net charge is 0, whereas the charge, on one plate would be equal and opposite to the other. And so this is typically what we're talking about here, that the battery acts as sort of a charge pump to move charges around. So here, this is our first look at current, which can be a little confusing. Current is defined to be the flow of positive charge, okay? And so we would say that current, as shown on this purple arrow here, would flow from the positive side of the battery through our capacitor to the negative side. First of all, positive charge doesn't flow, negative charge flows in most circuits. So in this case, the negative charge, the electrons, would be going backwards here. So first off, current flows from positive to negative. Electrons are obviously doing the opposite. So you might ask yourself, why is this? Well, the short answer is it was basically defined by Benjamin Franklin like 100 years before we knew what charge was. And we knew there was two types of charge, and we knew something was moving, so he just took a guess. We said positive was moving. He guessed wrong. Okay, cool. Why do we still use it today? Well, it turns out when you have like 200 years of knowledge built on something, it makes it difficult to change. And last but not least, there are actual circuits where positive charge does flow. So, take it for what you will. But positive charge is the definition of the direction of current, but negative charge flows the other way. Also, I'll make the caveat that no actual charge is flowing between these plates. Like, nothing actually goes across here, but we can, pretend like there's a positive charge flowing across the plate just as much as we can pretend that there's a positive charge flowing at all anywhere in the circuit. So, take it for what you will. Here, eventually what will happen is if you hook up a battery to a capacitor and give it enough time, the potential difference between your two plates, your voltage, ends up being the same as the voltage on the battery. For most capacitors, this does not take much time at all, but it becomes more difficult as you get more and more charge. So if your capacitor has a small area, it's going to be difficult to get it up to charge, or if you're using a particularly low voltage, it might be a little difficult. But, give enough time, which is generally like, you give it like 2 to 5 seconds. That's enough time. It will come up to the same charge as your battery. So, not charge, same voltage as your battery. But then you can remove the battery, and the voltage difference will just stay there between the plates. And so this is what we're talking about, that we can use this to store charge for later. So sometimes, literally in circuit, you'll charge a capacitor, then flip a switch to connect that to something else to discharge it. And one of the main uses for capacitors, besides leveling out, crazy charges and stuff, is used to very quickly dump it. Because, for instance, if you've ever seen one of those old disposable cameras, they have like a flash on, but flashes require very high voltages, and these voltages aren't put out by the battery. So how do we get that? Well, it turns out you just hook it up to a capacitor, and you hold down a button to charge the capacitor up. You just charge up the plates, but then you can discharge them through a different circuit and get a very different current flow with the same voltage. So, question 1. What is the capacitance of these two electrodes? Well, it's 4 times 10 to the negative 9th, or 4 nanocoulombs on this one, negative 4 nanocoulombs on that one. What's the capacitance? Well, capacitance would be Q over delta V. So, gives you delta V as 2 volts, gives you Q. So you do 4 divided by 2, you get 2. Hopefully that's straightforward enough. But again, if there's questions, let me know. Here, we're going to typically talk about the parallel plate capacitor, because that's what most of them are nowadays. And again, a parallel plate capacitor just has two pieces of metal that are pretty straight, and that way we get a nice uniform electric field between them. So here it gives us our electric field formula that we saw in the previous unit, or I shouldn't say previous unit, but before the test. The electric field is Q divided by epsilon naught A, so that's not different. And it's defined to be from positive charge to negative, because it's a vector. A is the surface area of the electrodes, and Q is the charge of the capacitor. So this isn't really anything new, it's kind of a review. This is a very fun picture though. This is a picture of not one capacitor, but actually 6. And it's obviously on a microscopic scale. Because it turns out for most capacitors, it doesn't really matter the thickness of the metal. You really just want a large surface area. So, as you can see here, it says that that's 1 micrometer in size. And so, we're talking about things that are really really small here, but you know, the same principles apply to this tiny structure as it would to any other capacitor. And one of the things you guys should note is that these are nice parallel plates, but it's probably not quite the plates that you are thinking of. That the positive electrode is this big fat gray area here, and the negative electrode is all these little areas here, and so that's why it's 6 capacitors, not just 3 or 1 even. But it's just a fun picture, I think. Alright, so the electric field of a parallel plate capacitor is related to the potential difference, delta V, and the plate spacing by this formula. So the electric field equals delta V over the distance. So if you know the voltage difference between the two plates, and you know the distance, you can also calculate that electric field. Notice there's some big vertical bars here because it's a magnitude calculation, because voltage does not have a direction and the distance does not have a direction. So you see it written with D or R, and I say that again because I don't want you thinking that it's a diameter or a radius. It's just a distance. And that will give you the electric field magnitude, but it won't give you the direction. Again, you're going to have to use your brain to use the direction. Then comparing these two different equations, we can get our previous equation for electric field and this equation for electric field. We can set them equal to each other and do magnitude calculations. We can get a different formula for capacitance. Capacitance is the charge over the voltage, which is what we already defined, but we also get another formula that says epsilon naught A over delta D. So it turns out we can calculate the capacitance of our capacitor is based on the charge and the voltage, or just geometrically, which is very, very important. Because epsilon naught is just a constant. Remember, that's the electric field permittivity. Area is the surface area of the plate, and D is the distance between the two plates. So surface area of one plate, just like this is the charge on one plate. And so that, when I say that's important, is because, like, if you were going to manufacture a capacitor, or say build one, like you have to do for this class later, the capacitance is really just based on the geometrical difference, that it's the area divided by the distance between your two plates. So if you had to build one, the capacitance should just be based on geometry. That's it. So that's pretty neat. The other thing I want to point out here is, for those of you who know a little bit about vectors, this is where us not talking about calculus is actually a detriment, because force and electric field are vectors, voltage and electric potential energy are scalars, and to go between them you actually have to do a very specific thing. In one direction it's a derivative, in the other direction it's it's called like a gradient. You can think about doing just a bunch of integrals. We don't do that in this class, but if you guys know calculus, you see these delta, like delta V over delta D, it should look kind of familiar, like, different, let's say delta displacement over time, like velocity is displacement over time. Well, those deltas in calculus become derivatives. And so this thing for calculus would become a derivative. We're not covering that in this class, but it's definitely one of those places that we're losing some information here. And so we can do all of this with algebra, but I feel like you lose a bit of the meaning when you do that. So just be aware that you're like, well, this algebra says I do this. In this class, just go, okay, I've got the algebra. All of the problems are designed to do it with algebra. You don't need any calculus at all. I'm simply mentioning this, kind of as an aside for anybody who happens to know a bit about calculus, because I find it very helpful, and you can't use it in this class, so whatever. Okay. A capacitor has charge Q. The plates are then pulled apart, so the distance between them is larger. After the plates are pulled apart, what happens? Well, if you look back at this, it says that it has a charge Q. Then we increase this distance. Well, what happens to it? Well, the charge increases, the electric field decreases, the charge whatever. Well, despite popular belief, the charge and field remain constant. Which again, if you go back to this formula here, oh, too far. Like C is Q over V. We've charged it. The capacitance can't change. Because it's like, yes, we did increase the distance, but the charge can't go anywhere. So the capacitance would change. Capacitance would change because the distance changes, but the charge doesn't change, and the field remains constant. So when I say go back, I guess I should have gone back to this one here. Because the electric field is Q epsilon naught over A. The area of the plates didn't change, and the charge didn't change. So the electric field would remain the same. So field remains the same, and the charge remains the same. So this is very important because a lot of questions they'll give you, or I'll give you, I'll give you stuff like this, and you have to be very careful because it's like, okay, if these plates are hooked up to another circuit, like a battery or something, then when we move the plates, then the charges are free to move. But as long as the plates are separated from any sort of circuit or battery or anything, then the charges can't move and they're going to stay there. And if the charges are stuck there, well, it turns out we could do some interesting things with it. Here it says we have a parallel plate capacitor constructed of 2 square plates, 1 meter on each side, which is a big plate, by the way, separated by a 1 millimeter gap. What is the capacitance of this capacitor? Well, capacitance is Q over delta V. Doesn't give us that, but it does give us the area and the distance, so we can calculate it as epsilon naught A over delta D. So that's what we're going to do. So in this case we get 8.85 nanofarads, which is a very small capacitance, and that's a very large capacitor. Okay. How much charge you actually get in there, again, depends on the voltage, but that is a very small capacitance for a physically very large capacitor. I mean, 1 meter, like that's bigger than any of y'all's desks. That's a very large capacitance. So now it says, okay, if we charge the capacitor to 100 volts, how much charge would be on the capacitor? Well, in this case, we know our capacitance, so we just simply multiply by our voltage, and we get 0.885 microcoulombs, which again is pretty small, but as we saw, coulombs tends to be kind of dangerous. And so 100 volts, you might think, it's ridiculous, but in that previous set of notes we talked about typical voltages. So on that picture, which definitely didn't show up on my notes, it said the voltage that comes out of the wall is around 110 to 120 volts. So 100 volts is easily obtainable. Yes. So I was going to do some demos. Obviously I'm not there today. There are videos of these demos online, so I would check those out. I'll try to link them around these notes in Canvas as well. But basically the demos are interesting because if you charge a capacitor up and then physically push the plates apart, charge up the capacitor, disconnect it from a circuit, then move the plates apart, the charge can't change. And so what's interesting here is that if you charge it up to a very high voltage, or not even a high voltage, but if you do that and then you push the plates apart, that has an interesting effect because the voltage actually depends on how far apart the charges are. And so what ends up happening here is you can actually change the voltage on the plates by simply moving them closer or farther apart without actually changing the charges on the plates, which is kind of neat. So that's just one of those things that I would demo. And there's actually pretty good links to that, I believe, through, I think it's MIT University that I've linked. But I digress. So anyways, now we're talking about dielectric. So what the heck is a dielectric? Well, a dielectric is just something that you put between the plates of your capacitors. You can almost think of like if you're building a capacitor, if I take a piece of metal and take another piece of metal, well, I can't just have them touching. They would just conduct electricity and not hold any charge. So you're going to want to put something in between them. Again, air is a pretty good insulator, and we can use that as a dielectric. But air has some problems, one being that it moves. So, you can be a little bit more consistent if you have just a thing. So you can almost imagine, okay, I have two pieces of metal and I stick a piece of plastic between it. Boom. Now I've got myself an insulator. Well, anything that we put in between that, we call a dielectric. It's something that's going to separate the charges. And it has to be an insulator because we don't want it to move. What's really interesting is insulators are insulators because they don't let the charge move. But typically when you put an insulator into this very strong electric field in between the plates, what ends up happening is that the atoms in the insulator will actually polarize. Okay? And so what happens is, it says right here, the polarization occurs when the atom's negative electron cloud and positive nucleus shift very slightly. They're not really going anywhere, but they're just kind of shifting a little bit in response to that electric field, because they're trying to sort of align with it. And so what ends up happening is the negative, from the insulator gets pulled closer to the positive plate, and the positive nucleus gets kind of pulled towards the negative plate. And so what ends up happening is that you end up having a electric field from the dielectric, which is actually opposite from the capacitor, which, vectorially overall makes the entire electric field weaker, which sounds on the surface like something you don't want. You're like, but I want a strong electric field between my plates. Yes, you do. But what's interesting here is because we've reduced that electric field, you essentially have from that insulator, the negative charges from the insulator being right near the positive charges of that plate. Well, now that distance is vastly decreased, which actually means now you can actually put more charge on those plates than you could otherwise. And then you can build back up to the default electric field that you had overall before. So it's really interesting. And so what happens here is, so we have this external field, as it shows right here, this E, shown with the pink arrows. And here it shows the insulator slightly polarizing. It's not really different, but you can see that the positive nucleus is more on one side than the other. And so that ends up giving it a negative, not negative, but an electric field in the opposite direction, right? So we have the applied field, and so this thing ends up aligning slightly opposite that, right? So it creates a uniform field like in a parallel plate capacitor, but one that's directed opposite, as I said. So a dielectric is anything you place between the two plates that's an insulator. The capacitor's electric field polarizes it, creates its own opposite field. The two fields give a net field in the same direction of the applied field, but smaller, thus the electric field is smaller with the dielectric. And so this is what I was saying. So here, this should make a little bit more sense. Okay, you have this net field, so that's these large pink arrows here going from positive to negative from the capacitor. But then you insert this dielectric here, and so you've got this smaller pink arrows going in the opposite direction, because again, the positive nucleus would be attracted to these negative charges out here, whereas the negative, electron cloud is attracted to the positive over here. So you get a smaller, notice they're drawn as smaller arrows in the opposite direction, which gives you a net smaller electric field overall, which is again a good thing because it's negative. That allows us to cram more charges in there. So that's what it says right here. Why do we want a weaker E field? Well, when the dielectric is inserted, the electric field between the plates decreases, which implies the potential difference decreases as well, but the charge remains the same. So therefore, we can increase our capacitance. all right? Because we didn't change the voltage. Your battery or whatever you have hooked up to it remains the same when you stick a dielectric in there. But because you have that dielectric in there, there's a weaker field, so you can actually grab more charge. So that will increase our capacitance. And so the way we calculate that physically is we have our capacitance formula, which is epsilon naught A over D. We're going to throw this kappa in there. And so kappa is the dielectric constant of whatever material you put in there, which would be determined experimentally, which is obviously different for other things. And so C naught represents the capacitance without a dielectric, or you can think of something that has a capacitance of, or kappa of 1. And so anything that has a higher capacitance or high dielectric is going to give you simply more capacitance simply by using this particular material. And obviously different materials are going to be different. So here you can see these dielectrics. That a vacuum has a dielectric constant of 1, because again, perfectly insulating. Air, pretty close to 1, not exactly. But depending on what you stick in there, you can see like Teflon or just a simple piece of paper has like 2 or 3. Water, if you could get it to not move, is pretty dang good dielectric. Has a kappa of 80. Strontium titanate, one of the best on Earth, has a dielectric of K, which is interesting because your capacitance really depends on geometry, but then you can just kind of throw a dielectric in there and say multiply it by 4, 8, or 100 times. So, and again, as it says right here, we're going to use 1 as a dielectric constant of air. So if it doesn't give you a dielectric, assume that it's air, probably not a vacuum. And there actually are a lot of capacitors that use air as a dielectric. Particularly those in something that has like a knob that you change, like say a radio dial, or like a volume knob. Like those things are typically interacting with your circuit by changing the capacitance, and so as you turn the knob, it actually rotates some plates, which changes the capacitance, but it uses air as the dielectric, so it allows it to change the size of the plates. Alright, so example, question 4. Parallel plate capacitor with a capacitance of 200 picofarads is charged to 100 volts, then the battery is removed. Then we stick Teflon in between. By what factor does the charge on the plates change? Well, if you remove the battery, it's not going to change the charge because the battery's gone. But what is the final potential difference? Well, it's the same as what the battery had on it, so it should be 100 volts. But when you stick that Teflon in there, it's going to end up changing things. So in order to find the actual final voltage, you'd have to figure out how much charge it has on there. So that's the first step. Calculate the default charge. So in this case, we know the capacitance is 200 picofarads. We know the voltage is 100 volts. So we multiply those and we get a charge of 20 nanocoulombs. Hopefully y'all are okay with me using nano and pico instead of times 10 to the 9th and times 10 to the negative 16th and all that. So then we calculate the new capacitance. So we calculate the new capacitance with the kappa in there. So kappa is 2, so that gives us a capacitance of 400 picofarads. So with the new one, with the same potential, or not same potential, same charge, because again it's not hooked up, we can find that by simply sticking that dielectric in there, we now have just 50 volts. What's interesting is that you can actually do the opposite. You can charge this thing with the dielectric in there. Let's say you charge it to 50 volts with the dielectric in there, then remove the battery, pull the dielectric out. Now the voltage is 100 volts. Which doesn't seem to make any sense until you realize you have to do work to, say move the plates or move that dielectric in or out. You have to do work. You have to apply a force over a distance, so it's going to change the energy of the system. And that is the end of the notes. So hopefully you guys got something out of it. I'm going to stop recording now.